Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Tableau, SAP, Crowdflower, IBM, and Alteryx, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you hadn't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Apache Spark and Agile Model Development, and that's going to be presented by Databricks. And before we begin, I'd like to briefly review the format for today's webinar. Today's event will be an hour long. We have one presenter who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and today's event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Richard Garris with Databricks. Richard is a principal solution architect at Databricks focused on helping clients with their advanced analytic initiatives using Apache Spark and MLlib. He spent 13 years working with enterprises in data management and analytics. Richard got his undergraduate degree at Ohio State University and a master's in software management from CMU. His previous work experience includes Skytree, Google, and PricewaterhouseCoopers. So, Richard, thanks for being with us today. I'm looking forward to your presentation. The combination of deep learning with Apache Spark has the potential for tremendous impact in many sectors of the industry. Apache Spark has quickly become a critical technology for data scientists to explore, understand, and transform massive data sets and to build and train advanced machine learning models. Now, machine learning and AI has begun to unlock new possibilities that are creating a competitive advantage for companies. However, companies continue to struggle to increase productivity of data scientists. The biggest hurdle to accelerate innovation has been the time to train, validate, and deploy models. So in today's Data Science Central webinar, we'll hear from Richard as he shares his various experiences across multiple industries, assisting customers with best practices for building deep learning pipelines, driving agile model development practices. So you'll learn from Richard today how to quickly train, validate, and deploy different models by leveraging Apache Spark and cloud technologies, to iterate through multiple models quickly by unifying the cloud infrastructure with big data processing capabilities, integrate workflows with data engineering and data science teams, simplifying, augmenting data to iterate on models, and finally, increase collaboration and agility within the data science teams to improve quality and decrease time to production. So, Richard, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Bill, and welcome everyone to our webinar today. Today we're going to talk about how Apache Spark enables agile model development. So many of you have seen this slide before, but as you know, AI, or artificial intelligence, is really changing the world. A few examples of this include a self-driving car, voice assistants, how you can have a computer that can beat the best players in the world at AlphaGo. When I was working at Google, I often saw the self-driving car as it navigated the various streets of Mountain View. And at one time, I was actually behind that car. The self-driving car was at a stoplight. The light turned green, but the car didn't go. So I honked my horn just like any other person would do, and I asked myself, does the car actually know if I'm honking the horn? Will it actually turn if I honk my horn at it? But again, just like every other computer technology, the car has to learn how to actually respond to that type of input. So it's very important to have that data to actually have that car learn. Likewise, both the Amazon Alexa as well as Google Home need to learn how to actually understand your voice and understand how to respond to your questions, as well as beat players at various games. It was now 20 years ago to this day that IBM Deep Blue was able to beat Garry Kasparov in a game of chess, and now we are able to actually advance that with Google's DeepMind technology to beat the best players at AlphaGo. So why is AI, in the forefront today? Why is it in 2017, 2018 that AI has really taken off? So one of the things that if you hear from other famous people in terms of the artificial intelligence community, people like Andrew Ng, it's really about the data. So the fuel that drives artificial intelligence isn't just new algorithms or the computers, it's really that big data. That's that key to the fuel that actually drives the rocket, which is artificial intelligence. So the hardest part of artificial intelligence isn't really about the actual algorithms themselves. It's really about big data. So a paper came out in 2015 from Google as well as a consortium of other academic researchers around what are the complexities of ML systems. So if you look around and you see this little box here in the middle, you can see it on your webinar screen, and this little black box that says ML code. So really that ML code is the extent of the problem for machine learning. It's really a very small part of the overall infrastructure. So all the parts around that machine learning that Google has developed in their Google Brain team really took a lot more effort to develop. Things like configuration management, feature extraction, serving infrastructure monitoring. Those are all bigger pieces of the overall puzzle of building artificial intelligent applications. Now, if you read the paper, one of the key tenets here is that anyone can build a one-time pipeline. I call it a Rube Goldberg-style pipeline for developing some type of artificial intelligent application, ingesting data, doing some type of algorithm, but maintaining that over time and having that, stand the truth of time is very hard. So really what companies are looking for really is platforms to build artificial intelligence applications, not just a point solution that they deploy one time and then it's very hard to maintain. So the first platform for really doing data analytics is really the data warehouse. So most organizations have a large data warehouse. Typically it's a Teradata, Vertica, maybe it's an Oracle-type database. It was really meant for a time when people really cared about historical analysis, looking at a look back at what's my revenue, what's my profitability, but it wasn't very good at doing forward-looking things like predictive analytics. It was also not designed really around things like agility, right? So the ETL process was very rigid. You had to use tools like Informatica, Ab Initio to actually ingest your raw data. To scale it out was very expensive. Typically, these are very hardware-based solutions, so you'd have very specific hardware as they deployed. And it was also limited to only SQL. It really couldn't do advanced analytics. So a few years after Data Warehouse came out, then SAS, SPSS, as well as open source R came to the foray. So most organizations that need to do some type of advanced analytics on these type of platforms would have to run a SQL query, extract the results, copy it to their laptop, and then run SAS, SPSS, or open source R to actually do the analysis. So that's not very agile. It takes a lot of time to go from a new theory to actually being able to pull data out of the data warehouse. It doesn't really work at scale. Additionally, from a rigidity perspective, even adding a single column to your ETL could take many months to do and then add it to your Snowflake or your star schemas. So it really wasn't built for being an agile platform for doing things like AI. The second generation was really the Hadoop data lake. So the Hadoop data lake changed the rigidity requirements around data warehousing. So it was schema on read as opposed to schema on write. So you could able to actually add many different sources to your data lakes. You could add files, you could add structured data, unstructured data. You can add things like Parquet for doing structured as well as images. But the problem was it became very messy. You lost a lot of the veracity of your data because it was very hard to keep a single source of truth. And then secondly, it was very hard to do data analysis because you had an ecosystem of tools that didn't really blend well together. So you want to do things like ETL, you'd have to use like Flume or MapReduce. If you wanted to do SQL, you'd have to use tools like Apache Hive or Apache Drill. In order to do things like machine learning, you'd have to use Mahout, and for streaming, you had to use things like Storm. So it became very hard to reason about, like, how do I get to an end-to-end flow around my AI or my machine learning pipelines, given all these disparate tools. So the third generation is really built around cloud, and this is really built around Apache Spark. So really what Apache Spark gives you is a single framework for doing all types of analysis required for doing your analytical applications. Everything from the ingestion side using Spark Core, doing things like SQL using Spark SQL, using MLlib or MLlib for doing machine learning, as well as doing Spark streaming for doing your real-time as well as your asynchronous streaming type processes. Additionally, and this is a Databricks feature, not Apache Spark, we also provide enterprise-wide collaboration using our notebooks and our collaborative workspace. So it gives you the ability to have much more agility with how you would build your end-to-end applications. So as an example, let's say a data scientist needs a new feature for their model. They can work with a data engineer. They can add that feature in a notebook, and then in the same day, or maybe in the same hour, you could actually start doing training on a new model. That's very hard to do in the first generation and second generation applications because you don't have that ability to work within your organization to develop that end-to-end pipeline and have one platform for doing those types of activities. So what is a data science platform? So Gartner, who's one of our partner companies at Databricks, defines a data science platform as an end-to-end platform for developing and deploying models. Now you ask yourself, what is a model, right? So a model is using sophisticated statistical models, machine learning, neural networks, text analytics, and other advanced data mining techniques to really provide some type of representation of what you're trying to model in the real world. So this is a definition of that. Really, it's a simplified, idealized representation of that. So as an example of this, everyone has, well, went to college or went to high school, has a grade point average. The grade point average is a summary of yourself. It's not necessarily, it says how smart you are or what you did in a certain class, but it gives an overall summary. It's a model of you as an individual and how well you did in your schooling. So I'm going to jump ahead to slide 16, and I'll come back to slide 15. But really, what does modeling really mean? So as an example of this, I'm doing a home remodel right now, and one of the key pieces of doing anything for a home remodel is really the plans. It's really that model of how we're going to actually change our home to kind of fit our overall vision. So that's very much alike to a model of a building when you do an architectural work. Similarly, you see this as well in computer science, both as a class. So for those of you that have done some computer science work, a class is a representation of a certain object inside of a programming language. This is an example of Scala. And so you see here, this is a class of an employee, and you see the attributes first name, last name, date of birth, as well as a person's grades. You can also have a method associated with this to actually do some type of operation on this class. And for those of you coming from a data warehousing background, you see here is your data model. So your data model is a representation of the overall attributes of your system, but it's a simplified representation. It's not the actual system itself. And so again, it's an example of a model. So I'm going to jump back to slide 15 and talk about modeling as it refers to in terms of data science as well as in machine learning. So model in that regard is really a mathematical function. It's the ability to take some type of input, learn some type of behavior or some type of result or a function, and have some type of output. So if you look at the decision tree model here on the left of your screen, this is an example of predicting the miles per gallon or the mileage of a vehicle. So there's many different ways to do some type of model. In this case, we're looking at a decision tree, which is really a flow chart. So it's really an if-then-else type statement. So in this very simple example, we're doing a classifier, which means you're trying a Boolean of yes or no. And you're trying to classify whether a car is going to be a high miles per gallon vehicle or a low miles per gallon vehicle. So as an example, if the weight is heavy, you say it's high mileage. If it's not heavy but the horsepower is less than 86, then it probably is high mileage. But if it's not, then it's low mileage. So it's a very simple example of a classifier. Another example of a very common model is linear regression or linear methods. So in this case, you have the simple function y equals mx plus b, where b is your series of coefficients. So whenever you create this type of model, what you're doing is you're looking through all your data, trying to learn the coefficients based on your data sets, and you'll plug into this equation, and that'll give you your result. This is typically used for things like targets. So let's say I wanted to predict not necessarily whether the car is going to have high mileage or low mileage, but predict the actual miles per gallon in terms of a number. So you use linear regression for that because it's a target. You're trying to predict an actual numeric response and not necessarily a yes or no answer. So again, we're talking about here artificial intelligence as well as machine learning, but there are other types of models that are used in data science. So things like statistical modeling, financial models, which are very common in terms of banking or Wall Street finance. You have financial models. You have graph models as well. So you always want to think about, as you kind of develop your problems in data science, not just thinking about things in terms of machine learning, but thinking about applying the right models and algorithms to your problem. A couple other examples, more domain-specific, is simulation models. Simulations are often used in oil and gas to kind of predict, the amount of oil that's going to be pulled out of the ground, as well as biological models, which are very common in pharmaceutical companies as well as bio companies. The whole idea is that you want to be able to model the behavior of a drug inside the human body to actually predict how well it's actually going to, cure some type of disease or to actually alleviate some type of condition that a patient has. So this is a quick view of the Agile modeling process. So we talk a lot about the model lifecycle. This is very similar to the software development lifecycle. So the Agile modeling process really should be Agile. So you really want to actually start with the first part, which is setting your business goal. Many companies actually, or many data scientists may not do this step, but it's a very important step because it's not just about creating some kind of cool personalization or some kind of cool feature in your application. It's also about tying that back to some type of business goal, whether it's increasing revenue, increasing customer satisfaction, reducing some type of risk, or reducing some type of cost. So you really want to tie that back to that business goal so you can have some smart metrics that will actually say that we're actually achieving our goal given our model. The second step is really understanding your data, which is really about domain expertise and understanding what data needs to be used to actually create your model. Then again, data science is a science. So a data scientist is a scientist. And because of that, you really need to create hypotheses and devise experiments and have some kind of rigor around that as you go about whatever you're doing as a data scientist. Then you go through the actual modeling process. You prepare your data, you train, tune, and test your model. You deploy your models to your whatever your environment is, and you measure and evaluate your results. And then you rinse and you repeat. So again, this is really an example of the life cycle of an Agile modeling process. This is very similar to Scrum or similar to things like CRISP-DM from as a data mining exercise. That whole idea is you want to have something Agile that you can apply to your overall data science projects. So why is Agile important? So often, there's cases where I work with companies and they say, well, I have this model and I've been working on it for 6 months. And I say, well, why haven't you, tested that model? How have you experimented with it? It's really important to get those models into an environment where you can actually validate the theories that you're using because that's how you can actually learn that they're actually effective in your environment. So using this quote from Charles Darwin from The Origin of Species, it is not the strongest of the species that survives, nor the most intelligent. It is the one that is most adaptable to change. So why this is important for our business is that, as we see today, companies that aren't adaptive to changes in consumer tastes, changes to the environment, changes based on their competition, it's very hard for them to survive in this business world. And so it's very important that as you apply data science in your organizations, that you make sure that you're applying agility as well. Otherwise, data science could actually be a net cost for you and not necessarily getting those kind of key benefits. So if you think about the goal of data science, and we go back to our examples of artificial intelligence, the goal is really to create the most accurate representative model to drive business outcomes. So what that means to you is that, if you're building a self-driving car like Waymo from Alphabet, or you're building some type of a voice assistant, the whole idea is you want to have accuracy. So for a car, you want to make sure it's very safe, and the way that you can guarantee safety is having a very accurate set of models so that the behavior of the car matches how it should be driving in the real world, as well as things like voice assistants, being able to ask a question of the voice assistant and always getting the right answer. So those are very complicated artificial intelligence or machine learning applications. And even a more simplistic view like fraud detection or ad targeting, With fraud detection, even single basis points of additional fraud capture rate or better or more accurate models can significantly reduce your losses as a bank or as a retailer. Similarly, if you're in the ad tech or the media space, higher click-through rates or higher CPM rates can yield huge benefits in terms of the ability to actually hit the bottom dollar of your companies. Likewise, and we're going to show this in the demonstration, is really about lead scoring. So you can think about lead scoring be about taking a lead that you don't know if they're going to actually convert over to a customer and converting them just a little bit better. It can yield a huge amount of benefit to your company in terms of both reducing your costs as well as improving your overall revenue. So you have model accuracy. Obviously, that's the goal of data science. The key thing about model accuracy is really understanding this type of equation. So there's really 4 key inputs that drive overall model accuracy. One is the number of experiments. So if you think about the experiments, every time you do an experiment, you learn something from it. A quick anecdote from Thomas Edison was that he did thousands of experiments on trying to figure out how to build a light bulb, but he didn't do 1,000 experiments and figure out how to make a light bulb. He did 1,000 experiments and found 1,000 ways not to make a light bulb. So every time you iterate, every time you work on a model, every time you learn something, you can get to a more accurate model by failing fast and learning from your failures. The other part of the model accuracy is really the number of examples. So having a lot of examples is key, and I'll talk more about that in a minute. The other key is model complexity. It's basically having a more complicated model, things like a deep neural network to learn the data that you have in your environment, as well as the number of features. So this is about the width. Now, one caveat in the asterisk here below is that accuracy only improves to a point. At a certain point, it will get to a point of what's called overfitting, which means modeling to the noise versus modeling to the actual what you want to learn, which means that the model has problems generalizing to new data. So you can only improve your accuracy to a point, but you always want to use these 4 ingredients to your overall recipe for creating your model to actually drive to higher accuracy. And I'm going to drill into each of these in the next few slides. So why more experiments? And I talked about this before. More experiments allow you to learn more quickly and fail fast. It allows you to experiment with different algorithms, features, and techniques. Apache Spark, as well as Databricks notebooks and other notebook-type features, give you a lot of flexibility to try a whole bunch of different tools in the toolkit, different algorithms, different featurization techniques, maybe using graph. So it gives you a lot of flexibility to use all those tools and have those available at your fingertips to do your experiments. It also allows you to more quickly adapt models to changes happening in your business. Why more examples? And so one of the things that we see with small data tools like Python, Pandas, or using things like open source R is most companies will subsample the data sets and then will create models off subsamples. Now, subsamples will actually limit your accuracy. It's been proven through this paper by Banco and Brill at Microsoft that having more and more examples actually yields overall more accuracy. Obviously, as you add more data, it does level off. It's a curve up and to the right. But as you add more examples, even small percentage points can mean a lot in terms of your overall accuracy of your model. The reason for this is the law of large numbers. So just like if you had a very small sample of individuals from a certain area and you want to try to figure out the average weight of people across the globe, if you only had a sample of 10 people, you'd have a very biased example of that. It could be inaccurate. But as you add more and more people to your sample, bias goes down, you get a bit more representative sample, and you'll actually have a more accurate model by having more examples of that. Why more complex models? So one of the things I see with people that are new to doing machine learning on bigger data sets is using the same simple model for bigger data. Why that's bad is because a simple model doesn't necessarily fit your data better. You're actually introducing bias as a data scientist into choosing your methods. So as a simple example, on the left box, you see linear regression with a very few data points, and you see a line of best fit through those points. So it's a pretty accurate line. You can see it going right through the middle. As you add more and more data points to this sample, you can see the line of best fit hasn't changed much. So if you add a lot more data and you have a line of best fit, just a simple linear regression model, you're not actually creating a better model. You're actually just fitting to the same numbers that you had before in your subsample. So as you get to a more complicated model, let's say you're doing some type of artificial intelligence application or using a neural network, you want to use a more complicated model with bigger data sets. So in the graph on the far right, you see here we're using nearest neighbor, which is a nonlinear, more complicated method. And you see 4 different categories, blue, orange, green, and red. And now you're actually mapping the data sets using, in this case, nearest neighbors. And so you can see here that each of these different lines are boundaries that are fitting to your data set. Now the problem with models that are more complex, they take more time to train, but they also give more accurate results. And then why are more features important? So features are columns for those people that come from data warehousing, but it's very important to have accurate features in your model. So an example of this in a fraud model, fraud modelers have, over the course of 30 years of understanding fraud, have introduced a lot of different calculations into the fraud model, things like the number of gallons of gas that you buy in a 24-hour period, because over time they found that individuals that steal credit card numbers will actually steal gas and launder gas because it's very hard to trace that. So that's one of the key features they use in their model, as well as things like distance from your home, the type of transactions you're providing, and those are key features that really drive toward more accurate models. As a case in point, I trained a very simple model. In this case, I'm using a measure called root mean squared error. It's simply the residual error squared and then taking the square root of that. So in this case, a lower number is a more accurate model. And so with a simple linear model, I trained that model and I got a 4.59 RMSE, so it's a decent model. If I use a more complicated model like gradient boosted decision trees, I got a 3.65, so it's obviously more accurate. Now, if I take away the most important feature from my model but still use a very complicated model like GBT, I actually get 5.63. So that's actually worse than my simple linear model. So the point of this is that when you think about how you do your machine learning, it's not just about using the coolest new neural network or coolest new ensemble tree method. It's also about having those accurate features, which involves you understanding your data sets as well as where to get your data, join those together, do your derivation of your features, and build that into your overall pipeline. So another part of agility is really about cloud. So one of the key benefits of cloud is the agility with which you can spin up compute, spin up storage, and have it available to you at your fingertips. It's also about the ability to make infrastructure being like software where it's completely fungible, and you can use that infrastructure in any way you please. So one of the things we've seen at Databricks in our Spark surveys is really a 10% year-over-year increase in Spark in cloud, and also an increase in number of Spark standalone deployments. So the key reason people do that is that standalone mode allows people to scale up the number of machines and the memory independent of your storage. So as you experiment with new models using more complicated machine learning methods, you'll need to have additional Spark compute. And you want to scale that independent of how you store your data sets. So one of the key quotes, and this came from a quote from The Economist: "The rise of cloud computing is rapid, inexorable, and causing a huge upheaval in the tech industry, and it really allows enterprises as well as companies to really innovate more quickly because of the ability to scale up and scale down their compute and storage." So this is from Crowdflower, which is one of the sponsors for Data Science Central as well. So Crowdflower did a survey and found that 3 out of 5 data scientists spend 80% of their time collecting, cleaning, and organizing data. So one of the key tenets on the webinar is really how do I make my data scientists, or who are often highly paid and highly skilled individuals, not be data janitors, but be true data scientists and have productivity really drives toward business results. So one of those ways is really to maximize the data scientist's time. So what limits accuracy really is that ability to have enough time for data scientists to do their modeling. So if you think about it, what limits our accuracy is really the combination of data size, model complexity, and then the experiment time, right? Because the goal of this is to have data scientists create more experiments and have more experiments to actually learn more and then create more accurate models. So with Apache Spark, one of the key things that we've done in terms of innovations is really the ability to create a linearly scalable system for creating your machine learning models. So if you have a model that takes 8 hours to train, as a good example of this, and you can quadruple the number of nodes to 4 nodes as opposed to a single node, you can actually reduce the amount of time it takes to train that model down to 2 hours as opposed to 8 hours. You can also likewise go from 4 nodes to 8 nodes and have the model take only 1 hour to train as opposed to 8 hours. So that time reduction really improves productivity of your data scientists so they can run more experiments and, again, come up with more accurate models. So I'm going to talk a little bit about Databricks and ML pipelines. So really the whole point of when we launched Databricks and have the data science platform known as Databricks is really to have an ideal platform for doing machine learning and data science. So it's highly iterative, it's very agile. It can handle a lot of different data sources, lots of dirty data. You can do all kinds of analysis, have a lot of tools in your toolkit to do your ML pipelines. It allows you to experiment with new methods. You can use different types of data as well as new features to minimize your error and, again, come up with more accurate models. So a little bit about Apache Spark MLlib pipelines. So we built pipelines based on the concept of scikit-learn pipelines. The whole idea is you want to create a pipeline that you can easily plug in and plug out different transformers and estimators based on your needs very quickly. This gives you a lot of a framework for doing experimentation that is hard to achieve if you're doing a lot of other kind of custom boilerplate code. It also allows you to easily explore your workflows and maintain the end-to-end platform. Much like our first example with Google, one of the key things that Google always says is you want to have something maintainable. So having a pipeline that you can understand and then you can also change in the future is very, very important. So I got a little bit about Databricks. So again, Apache Spark is open source. You can download it from the Apache Spark webpage. Databricks is the commercial company behind Apache Spark. We contribute 75% of the source code from people that work on staff at Databricks. And so one of the things we've launched within the Databricks platform is we call Databricks Runtime. So it's a layer on top of Apache Spark to make Apache Spark more performant in cloud. So things like Databricks I/O, which gives you the ability to read files from cloud storage layers like S3 much more quickly. In our latest benchmark that we publish on our blog, we show up to 5x more performance on Databricks Runtime versus open source vanilla Apache Spark. Additionally, again, I mentioned this in the past, we're really optimized both around linear scalability as well as cost. So one of the things that's unique with cloud is that if you decide to run a model and it takes 8 hours on a single machine or decide to run 8 machines for 1 hour, it costs you the same because you're leasing the compute. It allows you to, instead of spending the money, constraining your resources with one big machine and having all your data scientists fight over that, you can instead save money by having them more to work together and more agilely do their computations, but save on the cost because, again, you're renting the hours as opposed to buying those. The other piece of this is Databricks Serverless. So Databricks Serverless allows you to have auto-configured and elastic compute clusters built on things like EC2, and it gives you things like reliable sharing as well as fault isolation so data scientists aren't constantly running clusters and having to deal with failures as well as maintaining the infrastructure. So I'm just going to finish building this out. So this is our collaborative workspace. So if you guys have worked on notebook tools, the whole idea of these notebook tools is really to have a notebook built for Apache Spark and doing scalable analysis. So a couple of different key pieces for data engineers are really the ability to have fast, reliable, and secure jobs, be able to execute those jobs 30 to 50% faster, as well as notebooks that you can productionize in one click, as well as the ability to capture that log information. So one of the things that I love about Databricks from a job scheduling perspective is it snapshots the notebook. So at any point in time, if you have an error, you don't have to comb through logs, figure out what happened. You can actually see the actual code that executed and see the failure or see the slow performance and be able to fix it right away. For data scientists, the interactive notebook really gives the ability to interact with data in a way that's very conversational. So you can have a conversation with your data, and you can quickly iterate on your models and not be bogged down in using your ID or doing some back and forth with some type of infrastructure. So you can program typically in Scala or Python or SQL or R, as well as do things like in advanced analytics using things like graph, ML, or deep learning, and then take advantage of both built-in visualizations as well as D3, ggplot, or matplotlib. And lastly, for the business users, built-in dashboards. So oftentimes you want to have a business SME validate the model, make sure that it's accurate. And so you want to actually publish those as a dashboard so that your domain expert can actually look at that and validate that the model is accurate. All right, so I'm just going to build out this last slide, and then we'll get to our demonstration. So again, we talked about this. So you have Databricks Runtime, which includes Databricks Serverless as well as Databricks I/O. The thing to remember is it's 5x faster, and it reduces total cost of ownership by 70% by being both faster as well as more performant in cloud and taking advantage of things like spot prices and other things available to you in a cloud environment. The second piece of this is the collaborative workspace. So again, you can increase productivity by having a single environment for your data scientists to collaborate and build end-to-end Agile models and be able to deploy those quickly into production using our production job scheduling capabilities. And lastly, we wrap this all within enterprise security, so things like the ability to version control, share your notebooks, lock down your data sets. Data is an asset, and so you always want to be able to protect that data using best-in-class enterprise security. So one quick plug. So this week is Spark Summit Europe. So many of you are in the United States. I'm here in the West Coast, so I'm 8 hours behind Dublin, Ireland. But if you are up, early in the morning, and you want to actually view the live webinar, please visit the URL databricks.com/sparksummit/EU, and then we'll have the first keynote on Wednesday morning, Tuesday night. So please sign up, and you can see some of our live demonstrations here at our Spark Summit event in Europe. Lastly, and we'll get to our demonstration. So if you're interested in learning more about Databricks or learning more about Apache Spark or data science, please visit Try Databricks. We have Databricks Community Edition, which is free, as in free lunch. You can use it for as long as you'd like. You get a 6 gigabyte mini cluster, and you can try a lot of the notebooks here today, as well as other notebooks in our environment. If you have any additional questions, you can also visit databricks.com/contact-databricks and ask any questions you have of us or our team. So with that, I'm going to jump into our demonstration. Okay, so this is our demonstration. So we're going to demonstrate a simple lead scoring application. So lead scoring applies to many different businesses, and I chose this use case because it's something that most people can relate to in their businesses. So in this example, I'm using Databricks as kind of like our fictitious company. Well, actually, it's a real company. I work for Databricks. The whole idea is that we get a lot of inbound leads at Databricks from various companies as well as organizations, and so we need to do some combing through those leads to figure out which ones are good candidates to buy Databricks. So one of those ways is really to see if that company has a large IT budget. So I'm using an arbitrary number of 100 million to say that someone has a large IT budget. So I'm turning my problem from a regression problem of predicting exactly what the budget is to a classification problem. So I'm going to classify whether the company has $100 million in IT budget or less than $100 million in IT budget. So I only have a small sample of companies and their IT budgets. Not often that we actually get the IT budget of these various companies. It's not published typically. But for those companies that I do have the budget for, I'm going to put those into a table, and I'm going to compare with incoming leads to see what their IT budgets are. So at a high level, this is a technical solution I'm going to build. I'm going to ingest the data sets. I'm going to do some brief exploration. I'm going to create my features with SQL. I'm going to train a machine learning model, and then I'm going to evaluate that model. So the ingestion in this case is going to be from multiple sources. The first source, the list of companies themselves, are coming from, in this case, MySQL. It's a JDBC source. So here's where I'd actually load that driver, connect to that MySQL instance, and load up the data set. And here I can actually see the actual fields I'm pulling. So I have here the company ID, the company name, the sector they're in, the number of employees, the revenue, et cetera. And I can also look at that through my brief preview here, my HTML screen. So again, this is Databricks notebooks. You can also do this exact same code in open source Spark. That gives you kind of an idea of how to do that type of analysis. So here's my sample of IT budgets. Here I'm looking at a simple CSV file. So here I have the company ID as well as the actual IT budget for that company. So again, this is a simple text file. I'm storing this in S3 in this case, but it could be in any other distributed file storage layer like HDFS. So here I load it as an RDD. I'm going to use a case class, which is a Scala feature. Here I'm actually switching from my native Python notebook to Scala. And here I translate that text file, which could be messy data, into a simple data frame. And here I have the company ID as well as the budget. And here's my schema built into my notebook view. Here's where I join that in one line of code here. I do a join command in data frames, and I create a temporary view of all these different companies and their budgets. So you see here, these are real companies. Here's Nordstrom. Here's their IT budget. Here's the industry they're in, as well as other companies that you may be familiar with, like Amazon, BlackBerry, still around, and then Facebook. I can also join to other sources. In the spirit of time, I'm going to speed through a little bit of this, but this is an example of how you can create a Hive table. So if you guys are from the big data world, you understand Hive, and how I can join this with my Hive table to get other information like the region that this company is coming in from. All right, so I'm going to jump ahead a little bit. So I'm going to show a couple of quick features of Apache Spark that you can use in your businesses. One of the things I use is the Scribe, which gives you the ability to do a couple of summary statistics about your data set. So here you have the number of employees, revenue, and budget, and then you have mean, min, max of those features, as well as standard deviation, as well as counts. You can also do things like histograms. This is a built-in feature of our notebooks. So you have a data set like this, and I want to turn it into a histogram. One click, I can do that. So I can see here that most of the companies have a relatively small IT budget, and then as you get into much larger dollar amounts, like at the 100 billion range, you can see here that 100 million range, you can see that it's much smaller numbers of companies in that density. You can also do pie charts and graphs. You can do maps. In this case, I'm looking at where the companies are based, and mostly in California and New York. And you also do things like try to map data points using things like scatter plots. So in this case, I'm seeing there's a linear relationship between budget and revenue. So one of my theories is that revenue is a clear driver of IT budgets. So I can see here that as companies kind of get into the upper echelons of large revenue, so over 100 or let's say maybe 50 billion revenue, the IT budget is more scattered. So it's less predictable than here down at the very, very bottom. Okay, so here's where I'm going to create my features. I'm going to use SQL to create my features. The nice thing about doing Spark SQL inside of Databricks is you can create a query like this and have it instantly turned into a data frame. So a lot of data scientists I work with that use open source R or Python or SAS, they often have to run a SQL in their data warehouse, extract it, load it to their laptop, do some analysis. If they want to add a column, then they have to actually go back and run a query again and repeat that whole process. Here, if I want to add a column, I simply change this query, and then it's represented here inside of the data frame. So here are the features I'm going to use. I'm going to give the company ID, the industries the company they're in, the employees, the revenue, as well as the IT budget. So here's an example of how I've created a user-defined function in Python. Here I'm actually saying if the IT budget is greater than 100, then give me a 1.0 or a prediction of yes, that this company is a good lead, or 0. And then I register that with a Spark context, and then I can actually use that inside of SQL expressions like this. So again, here's my label. I've actually put my label here of 0, 1. It's on the left side. It's based on this function, again, that I've created. Here's where I'm actually using MLlib to do some light featurization or transformations. Here I'm where I'm using a simple regex tokenizer to split out the industries into tokens, count vectorizer to say whether it's in an industry or not. This is similar to one-hot encoding, as well as translate the employees' revenue into a single vector or an array that I can then use in my machine learning example. So here's where I actually create my model. So I save the model off to, in this case, S3. So if I want to actually reuse this model later in the future, I can take advantage of the location here. And these are my actual features themselves. So here's where I've broken out my data into different tokens, as well as broken it out into, in this case, vectors that I can then feed into my machine learning model. So here's my feature vector. Okay. So I'm going to give a couple examples of how you can train different models. So in this case, I'm using a binary classification evaluator, and I use a TVS, train validation split. You can also use a cross validator here if you choose to. In this case, I'm using simple linear regression, which this is the equation for, logistic regression. So here's my equation for that. And this is the actual model that I've trained. So again, these are all the coefficients for all the various features of my model. So the model is decently accurate. Here's my overall ROC curve, or area operating characteristic curve, so 0.78. So it's a decent model. I mean, I probably can do a much better model. You can see here, here's my graph of my my thresholds and the various ROC curve and how it would look. So I'm also going to use decision trees, and so decision trees are a way to do a nonlinear classifier. So again, the more complicated the model, the more accurate it is given my data set. So again, I save the model, and in this case, I get to a more accurate model. I get a 0.986. So again, you can also actually take a look at the data within the model. So in this case, I'm looking at all the different splits and why it's split at different features. Within Databricks, as a Databricks feature, you can also look at the model itself using a display command. So you can see here, this is the feature it's splitting on. Feature 1 is the actual revenue, which makes sense. So basically, companies over 1.47 billion in revenue tend to, in this case, predict that they're actually going to have high IT budgets, but not always. So we're going to look at these other features and why that is. So I did a little bit of some manipulation of the text output from my model. And here I actually look at the model using an if-then-else statement. And so what it's telling me is that companies that have over 1.47 billion in revenue tend to have high IT budgets. But if you're in computer software or financial services, you tend to have high IT budgets despite your revenue. But if you're in retail, industrials, or state and local government, then you tend to have low IT budgets, even if you do have a lot of revenue, which makes common sense if you think about it from a user perspective. So the last piece is I'm going to show you how to deploy the model, and then we can get to our question and answer section. So in this case, I'm actually going to score my model using a stream. So you can think of this as a way to work with your sales staff to make sure that you can actually productionize your models and do things like as new data comes in to actually do a prediction whether it's a qualified lead or not. So one of the things you can do with this is then create a dashboard. So if I jump over to my example dashboard and click Present, I can then have something like this for my Salesforce where it'll tell you the number of inbound leads for the day. Let's say it's 810. 288 of those were qualified, so a 35% inbound percentage. Here's the top leads by overall revenue, so Walmart's leading the pack, as well as you see some other big name companies here. Leads by sector, leads by state, as well as the ability to actually select your leads based on the state you're in. Okay. So give a quick example, and I'll also give a copy of this notebook so that you can play with this after the webinar. So with that, I'm going to go back. And jump into our Q&A section.
Well, Richard, thank you for that excellent presentation. And we'll get started with today's Q&A session. I want to thank the audience for their participation. We've had a lot of questions that have come in, and we'll do our best to get through them all in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Richard if you'd like to contact him following today's webinar. And joining Richard for the Q&A session, we also have Wayne Chan, who's been helping me offline here with your questions. And Wayne is the product marketing manager for Databricks. So Richard, Wayne, let's get started. Question from the audience about the notebooks, which created a lot of interest. At the high level, first of all, are these notebooks the same as, for example, an IDE? And on a more technical level, why did Databricks choose to develop its own notebook as opposed to using Zeppelin or IPython or one of the other notebooks that are available?
Yeah, that's a great question. So Databricks, when we looked at the notebook ecosystem when we first started, was really built around single machine algorithms, like doing things like pandas or doing things like single machine tools. So we really wanted to build a notebook tool that is really collaborative, so you could actually work together on the same problems in different geographies on the same notebook. It's almost like Google Docs is to Word. It really gives you a collaborative environment. A lot of those tools like Zeppelin as well as Jupyter or IPython are really single user tools. We also wanted something that we could make strong guarantees that works really well with all versions of Spark. So you can do things like attach and detach your notebook from your cluster and do your analysis against the Spark environment without worrying about compatibility or other issues. So it was a very conscientious decision. We're also compatible with open source notebooks like IPython. You can export and import IPython notebooks from your environment. But we really invested in it just to make sure that we had the best experience for people to run Spark in our platform.
Wayne, thank you for that excellent answer. Now, a couple of questions from the audience regarding what you described as, you used the phrase an agile machine learning platform to describe Spark. And the audience first is wondering, is that the same as an automated machine learning platform about which we're reading some these days? And either way, where in that model development process do you usually see the most improvement in time?
Yeah, no, it's a great question. So it's a little different than automated. Agile is really the ability to adapt things in a custom way using custom code. I kind of liken it a bit to software development. So you can have tools that automate the process of generating code, but it's not the same as the ability to be agile and adaptive and be able to adapt to new findings. So it's a little different than automated. And the second part of the question was,
where in the model development process do you usually get the most improvement from your agile process?
Yeah, I would say it's keyly in that featurization space. So back to that Crowdflower example of data janitors versus data scientists. Most data scientists spend 60% of the time doing all that featurization work. So really the power of both Spark and Databricks is really to alleviate a lot of that time to do all that featurization work.
Terrific. Well, thank you for that answer. Now, there are a series of questions here about when one should use Spark and under what circumstances. So let's start with a simple one. If I don't have big data, should I be using Spark?
Generally, no. So, I mean, the whole idea is that if you don't have a lot of data and you can do the same model in Pandas or open source R or any other tool like scikit-learn, then you can go ahead and use that. One of the things that you may want to consider, though, if you do expect a lot more data coming in or data volume, you want something more future-proof in terms of scalability, then you may want to invest up front in doing technologies like Spark in advance, but you don't need it necessarily for small data sets. Okay.
And then further on that topic, how does Spark work with legacy systems like mainframes?
There is actually a connector from, I believe the company is SyncSort, that actually connects to mainframe systems. That said, I mean, best practice for mainframe is generally to export your data sets as some kind of text file or other format that you can then load into Spark.
Okay. And then finally on this theme, a lot of us, when we think of Spark, we think of streaming data. So the audience asks, if I have real-time data, how do I do that with Spark?
Yeah, it's a great question. So if you think about real-time data, you can do one of two things. Either you can store that real-time data in memory and do real-time queries off of that, or you can stream the data in real time, ingest it, save it off to, let's say, Parquet, and then be able to query that Parquet table in near real time. Maybe you're going to have 10 to 20 seconds of latency between the time when the data arrives and when you can actually query it. So you can do both. Generally, my recommendation for machine learning to use historical data, use static data, because you don't want to actually have data changing underneath you as you try to model, because it's very hard to reason about your model if you're constantly changing data underneath you.
Well, thank you. Thanks for that explanation. Personally, I do see a lot of effort on the part of organizations with more than just a few data scientists to increase efficiency and effectiveness, get more done with fewer data scientists. So in your Agile model, in an ideal world, how much time would a data scientist actually be spending on infrastructure?
I mean, ideally it'd be, well, zero, but that's never the case. But the whole idea is that as you're a data scientist, you really want to focus in on understanding the domain, understanding the business problem, doing the mathematics behind the problem, as well as figuring out the right models, and doing very little time with infrastructure. So I would highly say that as much as possible, you want to get as close to zero on infrastructure as possible, and have that be another part of the organization's issue in terms of managing the infrastructure.
Okay, all right. And then in terms of time for production, what have you actually seen in terms of increases in efficiency and reduced time? Can you give us some examples?
Yeah, absolutely. So I work with a large gaming company. They went from taking 3 months to deploy a model down to just a few weeks, being able to actually agilely change their models and update them. I've also seen examples of various banks that could take up to 6 months to develop a model, and then take that down to just a few weeks to actually train the model, develop it, save off the model, and then republish that to run that in production, as opposed to having to recode that in their environment. So they can save a significant amount of time and be able to actually more quickly productionize those models in their environments.
Okay. Now, obviously, model development doesn't all involve deep learning, but deep learning's on the minds of a lot of us these days. When I use deep learning, does that mean I don't need to be as concerned about featurization?
Yeah, that's the theory, because a lot of the featurization is built into the layers of the neural network. But in all truth, I mean, an example of this is I was working with a large company, and one of the things they're trying to do is use deep learning to solve that problem. What they found was that their deep learning model couldn't beat simple logistic regression with a lot of really good featurization. So even though if you do have deep learning, it doesn't necessarily negate good featurization in your models. They usually go hand in hand.
All right, terrific. Well, thank you for that clarification. A couple of relatively deep technical questions from the audience. Is it possible to scale up compute nodes on the Databricks platform using I presume you have a GUI?
Yeah, so we have a self-service cluster management service. So you can actually do one of two things. Either you can specify the resources up front, a fixed size, and then run your model, and then increase the size later on if you need to add more resources. Or you can use our auto-scaling features, which gives you the ability to say, here's the minimum, here's the maximum, and then we'll automatically scale them up for you in our platform.
Terrific. Okay, that would be easy. And then another question of a technical nature from an audience member who has written some functions in Java or Python that are external and wants to know if he's in your notebook, can he call those functions external to the notebook?
Oh, yes, absolutely. So I didn't demonstrate this, but you can also create libraries. So you can either do one of two things. Either you can compile those as binaries and attach them to a cluster, or you can take that source code and paste it in a notebook, run it like I showed in the demonstration, and you can have those custom Java functions or Python functions available to you in SQL or in any other parts of your Spark code, and run those as you need to at scale.
Well, Richard, thank you so much for some great answers to some very good questions. For those of you that asked questions today that weren't answered, we'll be sending all the unanswered questions to Richard and the Databricks team so they can follow up with you following today's webinar. I have just a few quick announcements. If you would please mark your calendars for October 26th, that's this Thursday, and that's our next DSC webinar, which is data literacy, closing the data skills gap, and that'll be sponsored by Click. Also remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to Databricks for their sponsorship, as well as our speaker today, Richard Garris, for his insight into today's topic. This is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on October 26th. Have a great day.